Hey, all you cool cats and kittens. It's Carol at Big Cat Rescue.
Hey everyone, hope you're all doing all right. For your next assignment, we're going to talk about this drill block section view. You guys are actually going to recreate this, but you're only going to do the holes that are not threaded. So what I'm going to do is go over a couple PowerPoints to make sure everybody is kind of on the same page with how this is going to work, what these holes are used for, what the threads are used for, so on and so forth. And then I'll also share a couple of examples that I have, just a couple screws that I found in my shed to give you a little bit better understanding of what each screw looks like and what it might be used for. And so let's get started. Okay, so what we're gonna do is start with holes and hole notes, and I'm gonna flip back and forth between a couple different PowerPoints. So what we're going to start with are the definitions or classifications for the different types of cuts for holes. And two that should be pretty common sense, and you guys should already be familiar with, are through cut and blind cut. Now, blind cut you probably heard in a different way, or you just like didn't know that it had a name for it at all. Which is fine. A blind cut is a hole that does not cut through the entire thickness, and a through cut is the one that cuts all the way through. So blind just means you don't see an end point on the other side. The one that you guys might not have heard about, but have probably seen, is a clearance hole. So this is a hole large enough to allow the screw head and the driver to pass through. In other words, the screw is sunk down a little ways into whatever object it's being cut in. So they also have allowed for the screwdriver to be placed inside that same hole. That way it can be screwed in. I wish I had a good example of that here, but I haven't been able to find one around the house. But I know at school, the example I always use is the back of the keyboard. They want that screw head not to be protruding from the backside of the keyboard in order for the keyboard to lay flush on your desk. The next thing that I want to go through are the different types of heads for holes and for screws. So you have a countersink, which we've talked about. That's one where it's more of a cylinder, and then you have a cone, and then you have a counterbore, and that one's more cylindrical. And then you have a tapped hole, which just means that you have threads on your holes. So if you look over here at this example, this first one is going to be your counterbore. That's the cylindrical recess around a hole at surface. And then you have the following one is a countersink. That one looks like a little sink from the side here. And then the other outline here is going to be your tapped or threaded screw. Now, this shape over here is another example of a counterbore, but I want to talk about it real quick because that would be known also as a clearance hole, because that's going to give you the opportunity to put the screwdriver in to where you can get your screw all the way down to this level. And then here we have hole note symbols, some of which you guys are familiar with. Actually, you all should be familiar with them at this time with the train project. So you have your diameter symbol, your counterbore, which is that little half rectangle or a half square. You have your countersink, which is the V, and then you have the down arrow indicating depth. Holes a little more in depth. So you have a drilled hole, which is going to be a straight cylinder, and then you have your counterbore and countersink once again. A drill hole has usually just dimensions of height and width. Width in this case is going to be diameter, but from endpoint to endpoint on a width of a screw is going to be the same as the full diameter if you just did one revolution around the center point there. Then you have your countersink. So again, height is shown, and then your width or diameter is shown. And in addition to that is going to be your your width of the larger circle on top. Now, what is not shown here, which is typically shown, is an angle here for this line and that line. The reason why that's shown is because when you're drawing, let me see if I can draw real quick. When you're drawing an angle here, you can do the height between here and here, and that would set an angle for you. Or if you drew the top line and you knew your angle, and you had two angles from here, and you knew this height going this way and that height going that way, then you could cut away all this inside stuff, and you would have the intersection point there as where your angle would be. That's a little over explaining. However, you would either want to show the distance between this line and that line on your drawing along with the width at the top, or you would want to show the angle between these two lines here. Okay, those are just two different types of showing countersink. Sorry. Okay, and then your next one is a counterbore. Now here they show the difference, the distance to this line, but no angle, obviously, because it's just straight up on here, but it'd just be a cylinder in a 3D view. So then you have your heights there and your diameters or your widths there. All right, so now we're going to look at hole notes a little more in depth. You guys have seen the train project already, which was a good intro to this, but now we're going to dive a little deeper. So a counterbore symbol, or it's also known as a spot face symbol, is just this little half square. But what they do is a little strange. They actually flip-flop this note. So they put the counterbore symbol on the bottom when really normal people work from top down. So what they're saying is this portion here is representing this. So let me go in red here. This 0.25. And then the depth that it goes is 0.75. So that's going to be the whole thing here. 0.75. And then the next portion that they're talking about is here. So this counterbore section has a diameter of 0.38. So here we have 0.38, diameter of 0.38. That is a terrible 8. And a terrible 3. Anyway, you get it. And then this smaller section is going to go down 0.25. All right, so that would be your overall hole. All right, when you have just a blind hole, you're going to get just a normal plain diameter and depth symbol to your hole. Following that, you have a through hole. This is even less. You're going to have just the diameter and the word through, and that's indicating that it goes all the way through the line. The object. All right, so this is the countersink symbol. Here you have your V, you have your diameter, and you have your angle, your degree there, which is what I was mentioning to you guys earlier, where I way over explained it. And then you have your smaller diameter, and it's going all the way through the rest of the object. All right, so now we're going to talk about threaded holes. So threads can be added to holes for bolts or screws. There are several different types of thread series. Each is identified by their major diameter, the threads per inch, and the thread series identification. So here's an example. You have a 9/16 major diameter. You have 12 threads per inch, and the thread cap identification is UNC. So here's your, So here's your thread series. You have a UNF, UNC, UNS, and so on. And these basically are the types of threads that you have. So you will either have fine, coarse, special, extra fine, international standards, American national, internal and external thread. These are going to talk basically about, whether or not this is going to be for a machine, or whether or not this is going to go and be used as deck screws or concrete screws. Here's your unified national thread form. So you're going to have a rounded base, and then this just talks about your pitch from apex to apex, and then the depth of your thread. This is a side view here. You'll kind of see here. That's what it's talking about, the side view of your thread. And then American National Thread, they have a flat root, and that's just talking about the inside, where if you were to draw basically one cylinder, and you would just put a pitch around that, whereas this, you would have to draw a cylinder and take out grooves in that rounded root. That would be pretty hard to show you, but if you just were to revolve this image around a center axis, say maybe right here, if you would revolve that around, your screw head would look something like this. Wow, that's pretty bad. And then you would do the same thing on the other side. I'm getting better at this. Like that. All right, and then so your thread would come out like this, all the way around your shape. But there would be grooves in there. That's pretty bad drawing, but I digress there. And then on this side, instead of that, you would have just a flat line on both sides that the thread traveled around. So the thread would go around here like that. And it would just be flat on the sides. Okay. And then here we have thread annotations. So I'm not really expecting you guys to understand these thread annotations at this point, but what I do need you to know is why they're there and how you would find them. Now, the reason why we're not going to do threaded holes on this activity is because Onshape does not have the same database that Fusion 360 does. So half the class would get it, half the class would not. But essentially what you got is major diameter, number of threads per inch. You would have the threaded series identifier. You have your class fit. So here you have large tolerance, general purpose, low tolerance. And then the A is external or internal. And then you would have your thread depth last. Notes are usually shown to the exterior diameter of the circle. And you always have a center mark in circles whenever you place them. That way you know exactly where that center point is, and so where you can dimension to that center. The thread note or the hole note is going to be attached to show you that diameter. So this is a thread note of 5/16 with 18 threads per inch, unified, coarse. So this would probably be some sort of wood screw. The 5/16 tells you that it has a diameter of 5/16. So you would just want to convert that into a decimal, and you would be able to find the diameter of that hole. unified national, I'm sorry, let me go back. This next one down is going to be a metric label there. So here exactly what I just talked about. Skip that. We just covered this on the last one. And then here you have, this is the metric. Same type of readout for this in sequential order. It's just different numbers that you have there.
Hey, all you cool cats and kittens. It's Carol with Big Cat Rescue.
What I want to do now is go over sectional views because the drill block sectional view is obviously a sectional view. So you have three types: half, full, and an offset. A half section is one quarter of the part is cut away. The cutting plane goes halfway through the object, and this is done with symmetrical parts where you would like to show the outside as well as the inside details. Think of a brick and see an inside of it to see the center hole from the brick. Here's an example of a half section. So you have the line here that is known as your section line. It's going to cut out this quarter piece like cutting a piece of a cake. And what that allows you to do is see all the inside information in your isometric view, as well as you would be able to dimension now to each of these points on the inside view. It gives you more of a flat surface and allows you to see this inside offset here. Let me see if I can zoom in. There's technically from the center to this first physical portion of that would be the same as going from your center point to the line shown here. I don't think I would draw it that way, but that's what they have here. And that's what most people typically know for a section, excuse me. Notice how the cutting plane line runs through the center of the part. There is no arrowhead, so that's where you're going to start, going this way and down and over. Full section, the cutting plane passes fully through the object. So let's back up a second. In a half section, only a quarter is shown. In a full section, half is shown. The reason has to do with in a full section, you're already cutting the object in half to see the inside. So then, of course, a half of a half is a quarter. And that's where the key difference is. So here what we have is the shape is cut right down the middle, and then you see the inside of the shape. Most of you guys, I think, have seen this. Actually, all of you have seen it on the train project, but I think I've shown some of you, if you like put a plane through the middle and hit F7, you'll be able to see everything behind where that plane is, and everything in the front of it gets removed. A full section is a view that shows what the object looks like if it were cut in half. And then the cutting line with the arrows indicate where the view is going to be shown. So we're showing everything to the left of that line. And then what you do is you hatch the inside of the solid portions of the shape. So anywhere where there's not a hatching here is just a cutout. Right? It's not an actual physical shape. It's just where that shape has been cut. And then again, like I just said, everything where the shape is hatched is going to be a solid physical part. There are a lot of different line types that get used through dimensions and drawings, and a hatching is just another type of way to show a variation between different line types. Finally, you have an offset section, and this is basically where you have multiple circles here, and you want to show them and how they look, but they're not lined up. So what you would do is you would draw your your section line through each of the center points of those circles, and then it would show it down here correctly, but you would have to be able to recognize that this section line is not completely linear. There are different jogs and different levels here for that line. But it does essentially the same thing as a section view. And notice each of these has section AA, that's my A to A, and the scale shown. And that is just your view label. You wouldn't label a top, front, or side view, but you would label a section view. That way you know where it's being referenced to on the drawing.
Hello, you cool cats and kittens. It's Carol with Big Cat Rescue.
All right, so we're going to jump to dimensioning standards. I'll try to keep this short and sweet as we've gone through a few of these, and then this is a PowerPoint where if you guys want to know a little bit more, this is where you should go back to. That way you can actually sit down and possibly take some notes or just review it again to get a better understanding of dimensions and dimensioning. But it's something that you really only get good at by having repetitions of it, by practicing a lot. So this might not necessarily be the best environment to go over dimensions. And also it helps to have a mentor around that can, basically pass along conventions that they use. I know I learned a heck of a lot more when I worked for an architect in his office, when he could actually go through and tell me real life experiences and techniques that he used on a daily basis, opposed to when I was sitting in the classroom and just kind of reading off the paper what something should look like. So this is something that you will get better at over time, but not right off the bat. Rules and practices. Accurate dimensioning is one of the most demanding undertakings when designing parts. And so you'll have a checklist here. Here's some standards. The one that we'll be using is this ANSI standards. I have used military and DoD before, but that was on a special project, and that was like something rare or a one-time thing for me anyway. Depends on your career field if you'll see those again. ANSI is just an American National Standards Institute. They create the engineering standards for North America. I'll skip over a few of these. Here you have dimensions that comprise 4 components. You have your text, your lines, your arrowheads, and extension lines. And then somebody put all these different lines pointing at it right through the shape to make it confusing, but I think that's pretty straightforward. Extension line, extension line is extended from the view to indicate the edges referenced. And then you always leave a small gap there so they're not confused with the object lines. And they continue 1/8 of an inch past the dimension line. The dimension line is the line that holds the number that shows you what it is. You have horizontal dimension line, vertical dimension line, and you can have aligned dimension lines. In order to do that on Inventor, I know that you right-clicked and you could select a line. I would assume Fusion is pretty much the same and can't really speak for Onshape at this point in time. Arrowheads are just pointing to those extension lines because they want you to see where that extension line actually ends. And you can also use dots or datums. They are exactly the same. They're all interchangeable. Then you have your dimension text, which is straightforward, the numbers. Dimensions are represented on a drawing using 1 or 2 systems, unidirectional or line. And here's examples. So this is unidirectional, where the text is just facing upwards, and this is a line where the text matches where the shape is. There are 2 types of dimensions. One is going to be size and the other is location. These best put are going to be, you have a rectangle, you would need a size dimension for that, and you have a circle, let me do that not in green. You have a circle, and so your circle would need a size and a location. You couldn't just show the size of the circle. You would need to show that, oh, it's that far off and that high from the outside of my shape, from the corner. So I would need a measurement there, and I would need a measurement there, as well as the size measurement here, 0.25. All right. Here's a dimensioning checklist. Each dimension should be written clearly with only one way to be interpreted. A feature should be dimensioned only once. Dimension and extension lines should not cross. Each feature should be dimensioned, and dimension features or surfaces should be done to a logical reference point. Continued dimension circles should have diameters and arcs with a radius. There's a big difference there, guys. An arc is not a completed circle, therefore it's going to be used with a radius. We've talked about this multiple times. A fillet would use a radius. A circle, a hole, that's always going to use diameters. A center line should always be extended and used as an extension line. A center mark is another term for that. Dimension features on a view should clearly show its true shape. Enough space should be provided to avoid crowding and misinterpretation. That's very important. I've talked about that on like a construction job site. You don't want a builder to accidentally mistake a dimension that you have, and then he gets to the end of his building and the roof doesn't fit because you had a dimension that said 4 feet right next to a dimension that says 14 feet. Most of those guys are pretty sharp, they'll catch it, but occasionally, there could be confusion and you could cost a company a lot of money. And I guarantee you that would not make a boss very happy. We're going to continue here. You got extension lines and object lines should not overlap. Dimensions should be placed outside the part, and center lines or marks should be used on all circles and holes. That's a non-negotiable there. It needs to be on your circles. Linear dimensioning from feature to feature is known as chain dimensioning. It is commonly used and easy to lay out. It does have possible consequences in the manufacturing of the part. Tolerances can accumulate, making the end product larger or smaller than expected. What that means is if my part can pass or fail with being within 0.25 of an inch for each part, and each one of those has 0.25 of an inch on the max end of how wide it can be, at the end, if say it was 4 wide, at the end I would have a whole nother inch added onto my part, which could really screw up that manufacturing process. So not always the best way to lay it out. Here's an example of that. So chain dimensioning here is going from the start of this to that 0.5 and then adding up each of them each time. And that's just a tolerance note there. So this is, my tolerance is 0.01. I just talked about that with you guys. So let's simplify it. If it was 0.25 each way, then, this could go from being, or supposed to be being 1.5 all of a sudden to, or let's make each of these an inch. So it would be 3 inches wide. And if you had 0.25 on each of those, now your part's suddenly 3.75. And I'm sure that confused some of you, and that's okay. Here's just a further explanation of that. So here's where, you would change that and just place an overall dimension, and that will kind of lock in where your tolerances can go for this last portion. So it's basically saying, hey, you can only go 1.5 total. So your little stair steps here need to fit within that range. Here you have linear dimensioning, and the accuracy of the final product is determined by the dimension on the drawing. If all the dimensions originate from a common corner of the part, the object will be more accurate. This is referred to as datum dimensioning. Datums ensure the tolerance or errors in manufacturing do not accumulate. So if you think back to Puzzle Cube project, this is where we use datum dimensioning. And you guys really caught on pretty quick, and you did a really fine job of using datum dimensioning. I personally like this one a lot better because it is more accurate. And again, you don't want to leave that builder on the job site. You don't want to leave him with the ability to make any inferences from ambiguous dimensions here. Datum just means that you're going from one single point here. All right, so this is just basically telling you how it's locking it in place. So let's review a little bit. Your degree symbol, reference symbol is just parentheses. You have your diameter, your radius, your counterbore, countersink, depth, places, or by symbol. So if I have, 4 circles with a radius of 1 inch, instead of doing 4 multiple diameter symbols, I would just write 1 diameter symbol. I would put my X there and then say 4 of them. Plus or minus symbol is your tolerance stuff, center line, square, arc, and slope. Slope is used in architecture quite a bit. Dimensioning angles. Okay, so here you would use the coordinate method to specify the 2 location distances of the angle. Angle surfaces may also be dimensioned using the angular method by specifying 1 location distance and the angle. So here you have your coordinate method. That's basically saying, okay, I'm gonna go this far in this direction, and then I'm gonna come, basically where the convergence of these 2 points is gonna be how that angle is measured. And then from here, you can say if this line is a continuation, I'm gonna go 30 degrees from there. And what you could do is draw this line out all the way past and draw this line out all the way past. And then where their intersection is where that point would be. I usually do that method unless it's, because sometimes your point won't add up exactly on there if you try to do exact lines. And then when you go to extrude the shape, you'll have an opening in your shape and you won't be able to extrude it all the way. Here we have arcs and circles. This is really simple. You're using your radius or your diameter symbol with your depth, depending on what it is.